Welcome to day 4. We're going to look at all those trig functions we've been looking at. Sine, cosine, tangent, secant, cosecant, cotangent. I'm going to do some trig identities. So the first thing I'm going to look at is the Pythagorean theorem. Up my little right triangle here that I have on the side, inside the unit circle, I see an x, I see a y, I see a 1. So my Pythagorean theorem using x and y would be x squared plus y squared is equal to 1 squared, or just 1. But I do know this. X is equal to cosine of theta, and y is equal to sine of theta, base for the unit circle. So now I have cosine theta squared plus sine theta squared is equal to 1. And that is the Pythagorean identity. But I don't really want to write it with parentheses, so a better way of writing it would be cosine squared theta plus sine squared theta is equal to 1. That is the better way of writing it. Or sometimes we use the letter x instead of theta, so cosine squared x plus sine squared x is equal to 1. But this is addition, so it doesn't matter the order. And this is the number one identity in trigonometry because it's based off the Pythagorean theorem, the number one theorem of all time. Also, I could rewrite these and I would get cosine squared of x is equal to 1 minus sine squared of x when I subtract the sine squared over, or sine squared of x is equal to 1 minus cosine squared of x when I subtract the cosine squared over. Okay, so the one in blue is the number one identity, and the one in red I kind of manufactured by subtracting things over. So this number one identity, I could play with it a little bit. One way to play with it is to divide every term by the same quantity, or in this case, cosine squared of x. Once, twice, 3 times. And when I do this, cosine squared over cosine squared is going to be 1 plus, if sine over cosine is tangent, then sine squared over cosine squared is tangent squared x equals, and along with that, if 1 over cosine is secant of x, then 1 over cosine squared is secant squared of x. And look at that, I picked up another identity. 1 plus tangent squared of x is equal to secant squared of x. I could rewrite them a little bit and say that tangent squared of x is equal to secant squared of x minus 1, or 1 is equal to secant squared of x minus tangent squared of x. They are all the same. This time I'm going to divide every term by sine squared of x. Once, twice, 3 times, and when I do that, cosine over sine is cotangent, so this is cotangent squared of x, plus sine squared over sine squared is 1, and 1 over sine is going to be cosecant, but now it's cosecant squared. And there's another identity. Again, I could rewrite this and say cotangent of x is equal to cosecant squared of x minus 1, or 1 equals cosecant squared of x minus cotangent squared of x. Okay, so these are all my identities, all 9 of them that I have right here. But the main ones I should consider are the one here in blue is the big one, and the 2 in pink, and the other ones that are in the red, the green, and the pink are manufactured from those big 3. We're going to use them later today. Okay, here are our 3 graphs. The first two you better know. You should know that this is sine of x, this is cosine of x, and we briefly talked about this the one day that this is tangent of x. So let's talk about symmetry. Which one is even out of these 3? Well, I see y equals cosine of x is even, which implies that y equals secant of x would also be even because they go hand in hand. And then which ones are odd? Well, we know y equals sine of x is odd, and if I look carefully at this, y equals tangent of x is odd. The odd functions you could rotate 180 degrees. Cosine even could fold in half on itself. Therefore, y equals cosecant of x is also odd, and y equals cotangent of x is also odd, even though we never did that graph. So what does it mean to be even? What does it mean to be odd? Well, we talked about even means when I use opposite x values, I get the same y values. So if you look right here and right here, these are opposite x values. So f of negative x is equal to f of positive x. So f of negative x is equal to f of positive x. Opposite x's are getting the same y's. And what does it mean for a function to be odd? Well, we said for opposite x values, we get opposite y values. So right here is f of x, and right here is f of negative x. Well, this is equal to the opposite of f of x. And right here, well, this is f of x, and this guy right here is f of negative x. That is equal to the opposite of f of x. So f of negative x is equal to negative f of x. Okay, that's what it means to be even and odd. Yes, based on the symmetry, which even being folding over the y-axis and odd being a rotation of 180 degrees, but this is numerically. So how do I apply this to trigonometry? Well, I'm going to take those three functions that I have above, and I'm going to say cosine of negative x is going to be the same as cosine of positive x because it's even, and secant of negative x is going to be secant of positive x because it's even. Sine is going to be odd, so sine of negative x is going to equal negative sine of x, and tangent of negative x will equal negative tangent of x. And then conversely, cosecant of negative x will equal negative cosecant of x, and cotangent of negative x is going to be negative cotangent of x. So for the odd ones, sine and tangent, cosecant and cotangent, the negative input of negative x gives you the opposite result. And for cosine and secant, the even one, the input of negative x gives you the same result. And going back to what we know from the very beginning when we did trigonometry, we know that cosecant is the reciprocal of sine of theta, and secant is the reciprocal of cosine of theta, and tangent is sine of theta over cosine of theta, and that cotangent is really the reciprocal of that, so it's cosine of theta over sine of theta, which is really 1 over tangent of theta. So this is 1 over cotangent of theta. And these guys here technically is 1 over cosecant of theta. And this is 1 over secant of theta. But I really never use these. Because what I'm really trying to do is just rewrite everything as either sine or cosine. So I'm probably going to use this one a lot, this one a lot, this one a lot, this one a lot. I may use this one sometimes. I may even use this one sometimes. Maybe. But it's the whole idea about rewriting things as sines and cosines, because that's really the basic two functions, sine and cosine. So I'm going to use my calculator for this next problem, where I'm going to type in cosine of 20, sine of 70, cosine of 70, sine of 20, and see what happens when I get those results on my calculator. Make sure you're in degree mode on your calculator. So you can see I typed in all four of these into my calculator, and I see a nice little pattern here. I see that cosine of 20 and sine of 70 are the same result, and cosine of 70 and sine of 20 are the same result. And there is a reason why this happens. Okay, copying down the information from the calculator, I see how do these two compare. Well, I see that cosine of 20 degrees is equal to the sine of 70 degrees. And how do these two compare? Well, I see that the sine of 20 degrees is equal to the cosine of 70 degrees. And what's the reason why? Well, the reason why is, what type of angles are 20 and 70? They are called complementary. And what does the co part stand in cosine? It stands for the complement of sine. So that's the idea, that the complement of sine really means cosine. That's why these are equal. The complement of 70 is 20, so sine of 70 equals the cosine of 20 degrees. So how do we get complementary angles? Well, when I'm in degree mode, the complement of angle x is just 90 degrees minus x. 90 minus 20 is 70 degrees. That's why they're complements. If I had 18 degrees, 90 minus 18 degrees is 72 degrees. They are complements. They add up to 90 degrees. Complementary. Sum equals 90 degrees. How about when we're in radians? That's a little bit more difficult. In radians, instead of calling it 90 degrees, it's going to be pi over 2 minus x. That is the complement of angle x. Pi minus 2 over x is the complementary angle of x. So for all these problems before, below, this pi minus 2 over x is the complement. So the complement of sine is cosine of x. The complement of cosine is sine of x. The complement of tangent is cotangent of x, and so on and so forth. The complement of cosecant is just secant of x. The complement of secant is cosecant of x, and the complement of cotangent is just tangent of x. So don't get thrown off when you see sine of this pi over 2 minus x. It just means cosine of x. It's not really that big of a deal. So what is our purpose of doing everything we're doing? How are we going to use all these trig identities? We're going to do substitution. We're going to substitute equal expressions. Everything we've been doing, we've been setting up equal expressions. So everyone understands money, I hope. It's basically saying a dollar bill is equal to 4 quarters. Okay? When I have a dollar bill, I could replace one with each other. A dollar bill could go in for 4 quarters, and 4 quarters go in for a dollar bill, and they're all the same. So when we do all this stuff, if you ever see the expression 1 minus cosine squared of x, we said on the first page that is just sine squared of x. If you ever see cosecant of x, you could just rewrite it as 1 over sine of x. If you see tangent of negative x, well, tangent is odd, it becomes negative tangent of x. And if I see sine of pi over 2 minus x, well, the complement of sine is just cosine of x. And that's the idea. I'm going to see things that look complicated, and I'm going to put in something else that makes my life easier to simplify what I want to do. And all these items are on that summary sheet, so we're going to use that pink summary sheet to do all these substitution tricks. Get rid of something by rewriting it as something else to make my life easier. Okay, for the first two examples, we're going to use the Pythagorean identities to solve for what we need to solve for, and I understand I could draw a right triangle to get the exact same results, and maybe that would be easier. But for this one, I'm going to use the identity of cosine squared theta plus sine squared theta is equal to 1, mostly because every time I see cosine of theta, I can replace it with 1/3. So that gives me 1/3 squared plus sine squared of theta is equal to 1. 1/3 squared is 1/9 plus sine squared theta is equal to 1. I could subtract the 1/9, and I have sine squared of theta is equal to 8/9, and then I could take the square root of it, and I get sine of theta is equal to the square root of 8 over the square root of 9, which is just 3. Now I have to figure out tangent. Well, tangent of theta is just sine of theta over cosine of theta, and I have both of those quantities right now. So that would be radical 8 over 3 divided by 1/3. Now I learned a long time ago, instead of division, division really means to multiply by the reciprocal. So I could rewrite this as radical 8 over 3 times 3 over 1. These cancel. I get tangent of theta is equal to radical 8. Well, I'm given tangent of theta is equal to 2. Off that summary sheet, I see tangent squared of theta plus 1 is equal to secant squared of theta. So 2 squared plus 1 is equal to secant squared of theta. 4 plus 1 is equal to secant squared of theta. 5 equals secant squared of theta. I square root both sides. I get secant of theta is equal to the square root of 5. Also tells me that cosine of theta is equal to 1 over radical 5, just because they're reciprocals. So I know tangent of theta is sine of theta over cosine of theta. And based on what I know, I have 2 is equal to sine of theta over cosine is 1 over radical 5. I get rid of that by multiplying by 1 over radical 5 to both sides. And I get sine of theta is equal to 2 over radical 5. And therefore, cosecant of theta is radical 5 over 2, because I can just flip it by taking its reciprocal. Now I'm going to use my basic trig identities to simplify. Well, I would never rewrite cosine. Cosine of x is just cosine of x. But I could rewrite tangent as sine of x over cosine of x. Now you notice that the cosines cancel, and I get a final result of sine of x. So cosine of x times tangent of x is just sine of x. This one I'm going to rewrite. I'm going to say, well, cosecant of x is really just 1 over sine of x. That's a better way of writing it. Times, and this whole mess, sine of this whole mess, is really just the complement, or the cosine of x. I multiply it out, I get cosine of x over sine of x. And I have learned that cosine over sine is going to be cotangent of x. For this next problem, I see 1 plus cotangent squared, and off my reference sheet, I see that this is equal to cosecant squared of x, and it's all over cosecant squared of x, and something over itself is just 1. And then finally, I see this, so I could rewrite this as sine of x, and 1 over cosine squared off of that summary sheet is sine squared of x. Well, going back to algebra 1, something over something squared is going to be 1 over something. So this turns out to be 1 over sine of x, and 1 over sine is really equal to cosecant of x. That's how I can simplify those expressions. Again, I'm using my summary sheet. I know sine is odd, so sine of negative x is really negative sine of x times cosecant is also odd, so this becomes negative cosecant of x. But a better way of writing that is going to be negative sine of x times, a better way of writing this would be negative 1 over sine of x, because that's what cosecant is, just a reciprocal of sine. Sines cancel out, and I get negative times negative 1. I get positive 1 is my final result. This one here again, I know tangent is odd, so negative tangent of x. This whole thing is just the reciprocal, so that's cotangent of x. So I could rewrite that as negative tangent of x times, I could rewrite things with sines and cosines, or I could just write cotangent as 1 over tangent of x. I get the tangents to cancel out. I get a final result of negative 1. And this next one might be a little bit more work. Cotangent is odd, negative cotangent of x. Sine is also odd, negative sine of x. But secant goes with cosine, that's even, so that's going to be times positive secant of x. Where's my eraser? Get that x a little bit better. And then I do notice that I'm going to rewrite things as sines and cosines, so this would be negative cosine of x over sine of x times negative sine of x times 1 over cosine of x, because that's what secant is. I can see some things cancel. Sine, sine cancel, cosine, cosine cancel. I see negative times a negative times 1. So I get a final result of just 1. That's the way we manipulate all these trig identities, just by rewriting things. Okay, these next ones I'm going to kind of do some things where I'm going to pay attention, and sometimes when I divide I multiply by reciprocal. When I see this is just cotangent of theta, and I could rewrite this as 1 over sine of theta. Well, a couple things I'm going to do. I'm going to rewrite this as cosine of theta over sine of theta, and now I'm going to multiply by the reciprocal. So instead of dividing by 1 over sine, I'm going to multiply by sine of theta over 1. I see the sines canceled out, and I'm really only left with cosine of theta. So this whole mess to begin with just reduced down to cosine of theta. This next one I'm just going to rewrite as sines and cosines. So sine is still sine of x. Cosine is still cosine of x. But cotangent is cosine of x over sine of x. And secant is 1 over cosine of x. And now I could cancel some things out. I see a sine on top, I see a sine on bottom, I see a cosine on top, I see a cosine on bottom. When I'm done, I'm left over with cosine of x. So problem number 6 and problem number 7 led to the same result. Even though they're very different problems, they led to the same result. Now finally this last problem. This last problem is going to be a little bit of work. Probably the first thing I'm going to do is rewrite this problem as cosine of x, and then I'm going to rewrite tangent as sine of x over cosine of x, plus rewrite cotangent as cosine of x over sine of x. Okay, now I have this fraction, these two fractions adding inside the parentheses. So I need to add these two fractions together. That means I need a common denominator. That hasn't changed ever. I don't care if it's numbers, algebra, or trigonometry. I need a common denominator. So for this problem, the common denominator is just multiplying the two denominators together. Cosine x times sine of x. That's my common denominator for this problem. So that means I probably need to multiply this fraction by sine of x and this fraction by cosine of x. So when I rewrite this problem, I still have this cosine of x in front, and inside my parentheses I have a common denominator of cosine of x times sine of x, and my numerator, well, the first numerator will be sine of x times sine of x, which is sine squared of x, plus sign in the middle, and I get cosine squared of x. And I'm hoping when you see this, bells and whistles should go off, because that's the number one identity of all time. This is just equal to 1. So I rewrite this, I get cosine of x times 1 over cosine of x sine of x, because that whole numerator just turns into 1, and now I see I have a cosine and cosine cancel out. I've left over with 1 of sine over x, and 1 over sine of x is just cosecant of x. So this whole problem that I had to begin with, this whole messy problem right here, just turns into cosecant of x.